Thank you for all being here and welcome to today's online Forum on Robotics and Control Engineering seminar. Before introducing Dr. Tran, I will talk about the FoRCE a little bit, which is dedicated to provide high-quality outreach events and online seminars to reach broader robotics and control engineering communities. Thus, Tansel and I periodically invite distinguished people like Dr. Tran to give their talks on recent research results related to robotics and control. The aim of the FoRCE, connecting academicians, government, and industry researchers with each other through the research and education discussions. So we cordially hope that you will enjoy all the FoRCE talks and you will find them highly valuable for your own research interests. I also would like to add we have a support from IEEE Control System Society, where you can also find the past FoRCE talks and many other talks at the IEEE CSS video library webpage. I also need to mention about the WebEx, and you are all muted during the presentation. And if you want to ask questions after the presentation, you can do it by simply unmuting yourself, or you can write your questions to the chat box. And note that this session is being recorded and to be posted to the FoRCE website, as well as the IEEE CSS website. And jointly with Tansel Yucelen, we are very proud today to host Dr. Dzung Tran. And Dr. Tran is a research associate at the Air Force Research Laboratory, Wright-Patterson Air Force Base, since 2020. He received the Bachelor of Science degree in Mechanical Engineering from Missouri Science and Technology in 2014 and the PhD degree from University of South Florida in 2019. His research specializes in the distributed estimation, cooperative control, graph theory, and multiple networks with applications to multi-agent system, robotics, and dynamic data-driven application systems. And he is a member of AIAA and IEEE. So for all of you here, I would like to thank Dzung for participating in our forum as a speaker. And you can start whenever you are ready.
Okay, so thank you, Marvel and Tansel, for inviting me to the talk and for the introductions. So for the talk today, here the outline of the talks. We will start with the motivations, and then we will move into the detail of the generalized time transformation approach. We will also discuss the approach to design a finite time algorithms. This talk will mainly focus on application in multi-agent system. So we will also look at such an algorithms in detail together with how we implemented it on robots. Finally, we will end the talk with some concluding remarks. There are many applications that require the mission to be accomplished in finite time, such as landing an aerial vehicle on a non-stationary carrier. Other applications can be seen in multi-agent system, such as formation control, security patrols, search and rescue mission. In the applications, the robots or the vehicle need to do multiple tasks during their missions. Just like in formation checking problem, the vehicle first need to form the desired formations, then they track the target. Not to mention, if they encounter some obstacle or a narrow basis, the formation may need to be reconfigured in order to pass through. And these tasks need to be done in a user-defined finite time. Another common application is the simultaneous arrival problem, also called the servo attack problem, where multiple missiles need to engage a target at the same time. For that reason, we need to design the finite time algorithms. And finite time algorithm can be divided into three big groups. The first one, the settling time function exists, but the conversion time depends on the initial condition. In the second one, the conversion time can be upper bounded, independently from the initial conditions, and they are often called the fixed time algorithms. For the last group, the conversion time can be user-defined and independent from initial condition. What we will discuss today belong to this group, and within this group, several common methods that can be used to analyze the solution. They are the first one is explicit solutions. If possible, we can take a look at the explicit solution. The second tool is the comparison principle, and the last one is the time transformation method that we will go into detail shortly. For the time with the time transformation methods, we can decide the control algorithm such that the objective can be achieved in a user-defined finite time, a user-defined time, regardless of initial conditions. And these algorithms are also robust against perturbation. So we often assume that 3D parallel lines convert at infinity, but things could be different when we project them onto the 2D surface. Just like in this picture, you can see that these parallel lines converge at a single point that is called the vanishing point. The vanishing point is a term very popular in perspective drawing or in perspective transformation. And it's the point where the parallel line seem to converge. And similarly, the time transformation methods, we try to consider that the time at t equal to tau as if is as infinity. In other words, the idea that we try to transform the original system on a finite time interval onto a straight time interval, in that the time at t equal to tau is mapped to s equal to infinity. And therefore, on this straight time interval, we can use tools and methods that we are already familiar with, such as the Lyapunov analysis to analyze the system. Now for the problem formulation, we consider the system x dot equal to alpha times f plus g. Here x is the state vector, g is the bounded perturbations, f is a function that is continuously differentiable and globally Lipschitz. Alpha is a positive time varying scalar function. We call it the finite time gain function. And we also assume that x dot equal to f of x is globally exponentially stable. So why do we need this condition? So about this condition, you can think about it as your original aerodynamic system under the nominal control. That's it. You can design a controller to make your system exponentially convert to zero. And now you want to make it to convert to zero at t equal to tau, regardless of the initial condition. So for that purpose, our objective here is to construct a class of function alpha and the corresponding condition, so that we can guarantee that the solution x of t convert to zero when t go to tau. By the way, the materials in this talks is mainly from our paper, finite time control of a dynamical system based on a generalized time transformation approach, published in System and Control Letters. So first we need the generalized finite time alpha to satisfy the following condition. We call it the assumption one. Alpha had to be continuously differentiable on the finite time interval from 0 to tau. It had to be greater than m, where m is a positive value, and alpha approaches infinity when t approaches tau. An example for such functions a function that satisfies the condition is 1 over tau minus t, where tau right here is user-defined time. As you can see here, we choose tau equal to 5, and this is what this function look like. So for now, we move to the generalized time transformation function defined as theta of s, and it is equal to t, which is the time. The idea here is that we want to map t equal to 0 to s to equal to 0, and t equal to tau to s equal to infinity. And in order to do so, first we need to find a finite time gain function alpha that's satisfied the assumption 1 in the previous slide. And the second thing is that we need to obtain the transformation function theta of s from solving these differential equations. And theta of s also need to satisfy the condition here, which is theta 0 equal to 0 and theta of s equal to tau when s approaches infinity. So when we have theta of s under solving the differential equation and meeting the condition here, we can easily guarantee that theta of s is continuously differentiable and strictly increasing on the straight time interval. The second thing that we get out of it is that we define a of s equal to d theta over ds. So a of s is bounded, and the and it approaches 0 when s go to infinity. So in addition, we had the integral of h on the infinite horizons should be equal to tau. So this condition will be very helpful for the stability analysis later. I will not go through the detail of the proof, but you can, the proof is fairly easy, and you can look at it in our paper. So here the lemma 1 has established the theoretical connection between the finite time gain alpha and the time transformation function theta of s. From alpha, we can find the corresponding theta of s and vice versa. For example, with theta of s equal to tau times 1 minus e to the negative s, then we can find alpha will be equal to 1 over tau minus t. And another more generic form of alpha will be this one, and its corresponding time transformation function will be this. So here we can see a family of alpha and theta, which the parameter a and m being varied. The arrows pointing in the directions of increasing the parameter a and m, as you can see here. The interesting things here that the choice of alpha may shape the behavior of the system. We all know that at t equal to tau, alpha will converge, will approach infinity. So on the right end, they all look similar, but for different value of a, then the initial value of alpha are different. For example, with this blue curve, we can visualize that the system will work very hard at first because of the high gain, and moderate in the middle, though, and usually there is not much work need to be done at the end. But if we choose the curve with low initial value, like the one right here, then the system will work very little at the beginning. and increase the work loss gradually. And then at the end, if they add too much work to achieve the objective, the system will rush toward the goal. The reason because of the high gain at the end right here. Um, and also when A is fixed, we can see that the initial value of the gain just the same for on curve. But as M increase, the curves tend to be steeper at the end. We also recall that x dot equal to f of x is exponentially stable. So I often think that the system require a finite amount of energy in order to accomplish the goal. And alpha of t right here can be seen as the function that distribute the energy over a specific time interval. It also means that if you choose tau to the user defined finite time to be a small value, that energy will be released in a short time interval. And hence I believe that at some point we should take into account the limit of the activator when we use the finite time algorithms. So we are now ready to state the first resource. So we consider this better dynamical system x dot equal to a times f plus g, and if the finite time gain alpha satisfy assumption 1, and if there exists a corresponding time transformation function theta of s as stated in lemma 1, then we can conclude that x will convert to 0 at t go to tau. So for the proof, we can see that x of t can be rewritten in form of x of theta of s. And so we just define x bar of s equal to x of theta of s. And on the straight time interval, we take the time derivative of x bar, which is dx bar over ds, right? And using the chain rule, we have dx bar over d theta times d theta over ds. And finally, we end up with this dynamics. And so you can see that here z is the bounded perturbation. So g about and h of s right here. In lemma 1, we already, the second condition in lemma 1, we already say that a of s right here is bound. So if we consider the so the second term right here is bounded, so we can consider the second term right here as the input of the system. Furthermore, we had like x bar prime equal to f of x, the unforced system. It's either in unforced system, and that is already assumed to be exponentially stable. So we can conclude that this system is input to stay stable. Right? And one more thing is that we know from lemma 1 that a of h will approach 0 at s go to infinity. And that by the property of the input to stable system, we know that x bar of s will convert to 0 as s go to infinity. This is equivalent to x of t convert to 0 as t approaches tau. And so at this point, one may concern that x dot may grow unbounded on the time interval from 0 to tau. And so that is the reason we come up with the second theorem right here, which will state the condition to guarantee that x dot is bounded on the finite time interval. So there are two conditions. The first condition is that alpha dot over alpha square had to be bounded on the finite time interval. and there and its limit when t approaches tau had to be finite. The second condition is that we need uh, this system to be exponentially stable. And so now we look at the proof. You can see that x dot equal to alpha times f plus g bounded, and so we only need to show that r alpha times f, which we define as the vector r right here, is bounded over the finite time interval. And so we check the time derivative of r, and then transform it into the straight time interval, and this one is what we obtain. We know that G is bounded perturbations, F is leaches, and so the second term right here is bounded. By the second condition, we know that the unforced system right here is exponentially stable, and therefore we can conclude that this system is input to stay stable, and therefore R bar of S is bounded over the straight time interval, or R of T is bounded over the finite time interval. So we now propose a three-step procedure to obtain the finite time algorithm from the nominal one. For the first step, we design a controller for the baseline of the original system such that the objective can be achieved exponentially. I mean, like in terms of error dynamics, the error will go to zero exponentially. The second step is we need to find an appropriate generalized finite time gain alpha and the time transformation function theta f. So for the third step, we will introduce the finite time gain function alpha into the aerodynamics and go back to the control design process one more time to make sure that the final under the finite time controller, the final aerodynamics had the form like this. So to for illustration, we now look at some example. For the first example, let's look at the pendulum equation here. We can see that we had theta double dot plus psi of theta plus b theta dot equal to cu, where u is the control input. And let x1 equal to theta minus delta, where delta is the angle that needs to be stabilized. X2 equal to theta dot, and then we can rewrite the pendulum equation right here in the form of the system like this. We will use the backstepping method to decide the controller, and for that reason we choose z equal to kx times x1 plus x2, and then we can take the time derivative of this one, substitute the dynamics of x2 into that one, then we obtain this dynamic using the Lyapunov analysis. And through the control inputs at this one, we end up with the final form of the of the system at this one. We can see that we can always choose kx and kz to make the system exponentially stable. So we had just complete the first step. For the second step, we just choose a finite time gain alpha t. Just like I mentioned earlier, we have some kind of family. We can choose that one, or you can figure out one by yourself and can put it here. So here you can see that when you introduce alpha t right here, it change the structure of the original system, especially for example right here we have x1 dot equal to x2. So now x2 will be equal to negative kx times alpha times x1 plus alpha times z, right? And therefore, that's the reason we need to go back to the design procedure and to get the finite time controller once again. So here, uh, uh, based on this one, we choose z equal to kx times x1 plus k2 over alpha. And so we use exactly the same backstepping method, I mean like design procedure to obtain this final form of the control input. So under this probable controller, as you can see here, we had the simulation results for 4 different initial condition. So basically what we see right here, if we stack the vector x1 and z together, and then we calculate their norm during the mission. So you can see that with different initial condition, but they all convert to 0 at the user defined time t equal to tau equal to 1 in this case. And on the right, we can see that the corresponding controller control inputs of the system about it. For the second example right here, we will illustrate the control design procedure for sliding mode control and how we can go beyond the finite time interval. So let's consider this system. And then we define the sliding surface z, and let and then we check the time derivative of z, and choose the control input at this one. Then we will end up with z dot equal to negative kz times alpha t and z minus x1. Here we consider x1 as a bounded perturbation, and you can see that this one is already in the generic form of that we analyzed earlier. So we can say right away that under this dynamic, z will convert to 0 at a user-defined finite time tau. So at this point, I think you can see the idea. Usually the sliding mode controller is divided into 2 phases. The first phase, one is the reaching phase, and the second one is the sliding phase. And we use the time transformation methods to complete the reaching phase in a user-defined finite time. The rest is to design a nominal controller and switch to it at the time t equal to tau. So here you can see that we assume that the second state dynamics right here also subject to some bounded uncertainty or perturbation. Then we can use the standard method for design the sliding mode controller at this one. Then we combine the 2 controllers like this one, and you can see that at t equal to tau, we switch from the finite time controller to the nominal one. So to analyze the system under the controller with a term like this, we need to use the tools and methods for non-smooth system. I will not go into the detail here, but a similar system has been considered in our recent paper at SciTech. You can take a look at it. And we also recommend for the audience that for the non-smooth system analysis, you can take a look at the paper Lyabunov's stability theory of non-smooth system written by Savage and Baden. So for the simulation, we can see here that if we choose tau equal to 0.25, and you can see right here we had 2 different initial conditions. and they all convert to so at t equal to 0.25, the dash line is the sliding circuit. They all convert to 0, and then the nominal controller is kick in, and they are able to maintain the sliding circuit C at 0, and so the other two state X1 and X2 eventually convert to 0, and so the control input is bounded. We now quickly look at a simple multi-agent system finite time algorithms. Basically, what we consider here is just the leader follower algorithms, and we introduce the finite time gain alpha, and we choose right here is equal to 1 over tau minus t time m times t plus a. So the point is that I want to show you the under different choice of the finite time gain alpha, the behavior of the system may be different from each other. They all complete the objective here, which means that they read the tracking command at exactly 5 seconds. As you can see here, and X dot about this in both cases, but the behavior of the two systems are different, and I think it's interesting. It's an interesting research direction for the future when we find an appropriate finite time gain alpha to satisfy our I mean like to achieve the desired behavior of the that we want. So we now look at another time critical algorithm for multi-agent system. In particular, we first want to introduce the concept of multi-agent network as system. So basically, we have a group of vehicle or robots, so multiple agent here, and there are some floating agents denoted by the circle here. Basically, the floating agent only execute the consensus algorithms, and we also had the ability to access to some agent in the network. In that, we can observe their state, and we can also inject the control input to these agent, which we call driver agent, so that we can control or influence the behavior of the network. And so these driver agent will play the role at both inputs and outputs of the overall system. So the objective here is that we want to control the driver to drive the system to complete a text in a user-defined finite time. In the tool and methods that we use to design the controller, in this case, is the separation principle and the time transformation. So as you can see here, the floating agents it just execute the standard consensus algorithms. In the driver agent, we introduce the control input UI. Lambda right here, basically they adjust the finite time gain as we discussed earlier. And we explicitly consider it equal to 1 over tau minus t in this game. We also consider that the state of the driver agent and the outputs of the system. So we can write the dynamics of the overall system in the compact form at x dot equal to alpha times lambda times negative of the Laplacian matrix times x plus bu, and the output will be b transpose times x Here we consider the communication topology undirected and connected. And then we can easily prove that the bare negative Laplacian and B is stabilizable, and therefore negative Laplacian and B transpose is also detectable. This can be done by using the eigenvalue test. We now propose the control algorithms in this very generic form. U equal to K1 times X hat plus K2 times Z plus K3 times Z. Here, X hat is the state estimates, Z is the dynamic compensator state, and C is tracking command. K1, K2, K3, H, AC, BC1, BC2, and the gain matrix C that need to be designed. So we start the analysis by defining x tilde equal to x minus x hat, and then taking the time derivative, we end up with this one, where f equal to the Laplacian plus h times b transpose, and we can decide it to be a positive definite matrix. So so then we can stack x, g, and x tilde together at a vector r, and taking it time derivative using the under the probe controller, we end up with this dynamics. So you can see that this metric is m and this one is n. So our goal is that is to design the gain matrix C such that the term right here will convert to 0 at t go to tau. In other words, R of t will convert to negative of m inverse times n times c. And this one will capture the control objective. So in order to do so, the first thing that we had to do is we had to make sure that M is invertible. To be more specific, it had to be Hurwitz in this case. And so by looking at the structure of M right here, and you can see that we can decompose it into submatrices like this. And it had the structure of an upper triangular matrix. And so for M to be Hurwitz, we only need to show that M4 and M1 is Hurwitz. And F is positive definite. And so negative F or M4 right here already Hurwitz. So what we need to do here is that we need to decide the gain matrix C to make M1 to be Hurwitz. Once again, looking at the structure of M1, we can decompose it. We can write it in terms of the sum of the two matrices C, and then finally, it had the form of A tilde plus B tilde times K like this. So for M1, so we can say that if A tilde, if the pair A tilde B tilde is stabilizable, then we can always choose K1 and K2 such that the metric M1 is Hurwitz. And we figured out that for A tilde B tilde to be stabilizable, we need two conditions. The first one is negative Laplacian B is stabilizable, which already satisfy. We already showed this at the beginning of the algorithms. So the rest is that the rank of this metric had to be n plus p, where lambda is the eigen value of AC. And so we need to decide, we need to choose AC and BC1 so that this condition is satisfied. So now, after we have M1 also always, then we need to prove that this term will convert to 0 at t go to tau. So for that purpose, we define this term at Q, and when we take it time derivative and substitute the dynamics of at R, which is this one, into the equation, and this one what we end up with. So CD right here is actually the C dot, the time derivative of the command, and we already assume that this term is bounded. And so you can see that this second term is bounded. M is whole width, and so the first term right here is exponentially stable, and it's exactly the generic form that we analyzed earlier. So we also can conclude that Q will convert to 0 as t go to tau. Okay, so they no need to go through the proof right here, as we already proved it earlier. So for the boundedness of R dot, we can use the earlier theorem 2, and we found that the fancy M matrix right here equal to I plus alpha times M had to be also whole width. And to guarantee this metric to be whole width, we need to choose alpha such that it is greater than negative 1 over the maximum of the real maximum eigenvalue of M. I mean the maximum of the real part of the eigenvalue of M. And so for the simulations, we consider a path graph with 4 agents. The agent 1 and 4 are floating agents. 2 and 3 are driver agents. We also consider that the tracking command had the dimension of 2 with represents for the 2 targets, C1 and C2. And we also consider that the conversion time tau equal to 5 seconds. We already saw that this term, the limit of this term at t equal to tau equal to 0, but actually R consists of x, z, and x tilde, but we only care about x tilde. We only care about x in this case, and so we decompose the matrix M and N to derive that at this result that x of t will convert to negative this metric times c when t go to tau. So we want, because we had the command had the dimension of 2, so the C1 and C2 can be the same or it can be different. When they are the same, the problem become a consensus problem. But when they are different, we want them to split the network and track those two target. And so we would like to choose this matrix to be this one in order to split the network. But and so from here we work backward. As you can see that M1, N1 right here, they are related to the metric gain, the gain metric state that we need to design, and so we work backward in order to find the gain metric state. And so for the results of the simulation, you can see here we had the dash line represents the tracking command C1 and C2. The dot line is a little bit hard to see here, but they are the estimated state. and the solid line at the actual state of the agent in the network. And you can see that they are able to split into the two groups um, and convert to the tracking command C at the same time, T equal to tau equal to 5 seconds. And so the control input evaluated. So uh, everything looked good so far, so we want to do an experiment to further justify the probable algorithms. So we consider exactly the same scenario with 4 mobile robots. Uh, yeah, and we also had 2 moving targets. We also adjust the conversion time to be 15 seconds in this case. So here the experiment setup that we had at USF earlier, that we had the motion captures camera system mounting at on the ceiling, um, so that we can obtain the position and orientation of the robots. We had a group of 6 camera robots, and they had marker on top so that the mocap system can recognize them. And we also had a workstation to process the information. The robots that we use in this experiment are the camera robots. They are different short drive robots. And here is the structure that we use to implement the proposed algorithms. So the proposed algorithms is a distributed algorithm, and it's put at the top level. So it will calculate the next point that the robot need to reach, and it is kind of like the waypoint. And those waypoints are passed to the go-to-go program. This program will generate the linear and angular speed for the robots to reach the waypoint. And this speed can be easily converted into the left and right wheel speed for the robot. So when the robot receives the commanded speed, right, the robot will once again translate this speed into the command for the motor and make the robot move. The motion capture camera system will update their position and orientation for the next iteration. So as you can see here, we had the 2 targets at the top and a group of 4 robots at the bottom. And under the proposed control algorithms, as you can see here, the robot are able to form 2 different groups, and then they hit the target, the 2 moving target at the same time. So for concluding remarks, in this talk, we already introduced the generalized time transformation methods that can be used to design the finite time algorithms that have the objective can be achieved in a user-defined finite time, regardless of the initial conditions. The algorithm are robust against the perturbations, and the desired virtue is also provided. We also look at an application in multi-agent system which relate to the network as system, in that we can influence the network behavior through the driver agents, and the network can commit a text in a user-defined finite time. Finally, I would like to thank my collaborators for this project, including Dr. Tansel Yucelen, Dr. Burak Sasima, and Denise Kutalo. And that's it. Thank you.
Thanks, Yang. It was excellent presentation with all the information on the finite time convergence. So yeah, it's an important solution for many applications. I really enjoyed. Well, it's time for the questions. If you have a question, you can do it by simply unmuting yourself, or you can pass your question to the chat box. Well, seems that no questions or comments, but we can wait.
In most of the presentations, it happens actually. They online audience usually, I mean, it's based on my feedback. They like sending emails.
Yes, sure.
There is one message.
Oh, Islam just thanks to him.
Oh, okay.
There is one question. So, thank you for a very nice talk. I want to ask you, show the results till time capital T. What about after time capital T?
Yes, just like I mentioned in the presentations that for critical, I mean like usually we can divide the application into two class in finite time. One of them is critical time application, just like in the server attack, right? You hit the target in finite time and then you don't care what happened after that. And the second one is that you can extend it to infinite horizon by at the time t equal to town, you jump to you switch to a nominal controller, just like I did in the sliding mode controller. I use the finite time algorithm to derive the sliding surface to 0 in a user defined finite time. After that, I will switch to the nominal control in order to stabilize the system afterward. Hopefully that answer the question.
I think it does. So if you have follow-up questions, you can still use the chat. There is one audience. I'm not sure if the pronunciation is correct, but Giovanni.
Yeah, it's Giovanni. It's Italian. Hello. I'm trying to turn my camera on just to be more polite, but apparently it doesn't work. I'm sorry. Yeah, I'm speaking from Italy. I do research in robotics. I wasn't able to follow from the very beginning, so I'm sorry if I'm asking something that perhaps was already spoken about. My question was regarding how and if eventually the method you described can take into account saturations on the inputs, because if you achieve finite time, control, and regardless of the initial conditions, as you announced, of course, depending on the initial conditions, you will have different control effort. And I was wondering if you have saturations on the inputs, if there is a way to take them into account in the design process or not.
I think it's an interesting questions, and so just like I mentioned in the net in the presentation, like I often visualize that basically what we do there is that we try to convert a exponentially stable system into a finite time stable system, and so the thing is that for the exponentially stable, I often visualize it that you need a finite amount of energy in order to complete the text, right? And so when you choose the user-defined time to be short, to be small, then that energy had to be released in a short amount of time, and so this may for some application it may be impossible because it will saturate the controller. So I think the practical use of the finite time algorithm is that we should know the limits of the robots or the system, and kind of like I think in the future it will be interesting if we can kind of like investigate kind of like if we have a map a kind of the accessibility region, which means that if you are in a certain region that is close enough to the target, or then you can take into account of the saturation in that way. I know that it's not very clear here, but because consider the for the normal even with the normal control problem, if you consider the saturations of the activator is already a hard problem.
Sure.
So, Giovanni, Young, if you don't mind, so I pasted a paper to the chat. Basically, Ehsan Arabi. I mean, when let me give you a little story. When I received this grant from Air Force, Young and Ehsan, another researcher, they worked on this topic with me. After Ehsan graduated, he wrote a paper on prescribed time convergence with input constraints. I believe he started to touch this problem in his 2020 paper.
Okay. Yes, thank you very much. I just saw it. I didn't notice earlier. I'll have certainly a look. I'm really very eager to read this, and of course, if it's okay with you, I will possibly come back to you by email in the future to talk this over.
Yes, sure, for sure. Yeah.
Okay. Yes. Thank you very much.
Thank you for your question.
Any other questions or comments for Young? Well, I think we can conclude the session. Young, thank you again for participation, and thanks to the audience for the participation as well.
Thank you.
Yes, thanks to you all then. Bye-bye.
Have a great day. Bye-bye.
Thanks, everyone. Bye.